Good morning, good afternoon, and good evening, everyone. Welcome to our webinar number 3 regarding the electrical impedance tomography. And today we are going to be talking about the esophagus pressure measurement and the importance of the esophagus pressure measurement in the clinical practice and how PulmoVista 500 can support the clinical practice and various clinical interventions. So today, my name is Margarita Singer, and I'm the Regional Marketing Manager for Intensive Care at Dräger Middle East and Africa, and I'm very excited to welcome our guest speaker today, Mr. Dräger Teschner, who is the Senior Product Manager in the field of intensive care at Dräger. And he's one of the most knowledgeable persons about the EIT and about PulmoVista. And today, Echo is going to be sharing his technical expertise and his clinical knowledge in the field of electrical impedance tomography and how it can support the improving patient outcome in the critical care. So again, a few organizational things. If you have any questions, we are going to have a question and answer session. So during today's webinar, we're going to spend probably 45 to 60 minutes on a theoretical lecture. We're going to have a short break, and then we're going to have a demonstration. At any point of time, if you do have any questions, please type them into the question box, which is located on the right side in the GoToWebinar chat box, and we will dedicate the time to address your questions. And now I'm very excited to give the words to Eckhart, who is going to share his knowledge and his expertise with us today. So Eckhart, the stage is yours, and thank you for being here with us today.
Big pleasure. Thanks very much, Margarita. Yeah, also welcome from my side. My name is Eckhart Teschner, and as you can read here, we will talk about the monitoring of transpulmonary and esophageal pressures, and especially how this monitoring is realized with the PromaVista, which originally is, of course, a EIT monitor, so electrical impedance tomography, and I've talked about that, those aspects in the last webinar. And I also don't know how many of you have already worked with EIT or know about EIT, but that was the subject of the last webinars. And today I'll focus on esophageal pressure measurements and monitoring of the transpulmonary pressure. As you can see from my vita, I would call myself a specialist in EIT, definitely, because I'm dealing with EIT since a very long time, the last 20 years. And we realized that apart from the regional information that is provided by EIT, it's also very important to understand and distinguish the transpulmonary and the esophageal pressure, because they are providing a different information to what is available today in all ventilators, which is airway pressure. And so in this presentation, and as I said, I don't know how much knowledge you already have about these kind of things. I have to admit, I gained my knowledge only over the last few years in this respect. So, but just to get into this subject of esophageal pressure measurement and why it is considered to be very relevant in the clinical practice, I'd like to start with a kind of analogy, which hopefully highlights what is the difference between the transpulmonary and the airway pressure. So I chose the example of a tire and a tube. of a bicycle, because here in Germany we are doing lots of bicycling. So this is at least something, this scenario with a flat tire and the bicycle, something at least people in Germany are very familiar with. So to use this analogy, the tube actually represents the lung, and the tire the surrounding chest wall, which kind of defines the limit to which the lung, or the tube in this case, can expand. And the pressure inside the tube is kind of corresponding to the airway pressure. So you can imagine when you are pumping up a tube, when you have a very stiff tire, there will, when the tube touches the surrounding structure, which is a tube, there will be no change in volume anymore when the pressure increases. But of course, because the tire prevents that the space gives way to the increasing pressure and the expansion of the tube, of course, then in such a scenario, the pressure inside the tube increases dramatically. So that means when we have a very stiff tire, we could say, okay, the tire has a very low compliance. Or if you want to take the term elastance, which is a reciprocal of the compliance, we can say a stiff system has an extremely high elastance. And sometimes it's a little bit confusing because elastic material, somebody would think this is very tangible, and but the opposite is true. A high elastance means it's a very stiff structure. So as we know from a tire, the tube simply can't expand because the tire is preventing the expansion of the tube when it's filled up with air. And when the tire, and that is basically the condition at this location A, where the tube sits inside the tire. When you see on this picture the condition where the tube is outside of the tire, in such a case, then the tire, of course, will expand dramatically. And what can also be displayed here is what you can probably easily imagine when you have a kind of inhomogeneous lung condition. Then there will be extremely high local shear forces at those conditions with the inhomogeneities. And that again is something that we can, of course, much better represent with region information as delivered by electrical impedance tomography. So now to convert this scenario on the lungs. We already can imagine that depending on the elastance of the tire, or in our case, the chest wall, it depends how the airway pressure will actually distend the lung. Because the airway pressure distends both the lung and the chest wall. But without this information on esophageal pressure, it remains unknown to which extent the lung is distended. But that is, of course, what is most critical for the patients, because we want to avoid ventilator-induced lung injury. So the monitoring of the airway pressure, which is a substitute of the alveolar pressure, basically the pressure inside the tube again, it only allows to determine the elastance of the whole respiratory system. But as you can see, and I should maybe activate the pointer here. As you can see, the elastance of the respiratory system is defined both by the lung elastance, which is this structure here, of course, and the surrounding chest wall elastance. Yeah, and that means the airway pressure is distending both structures, the lung and the chest wall. And the stretch on the lungs is not determined by the elastance of the respiratory system, but only by the lung elastance. So in the paper that is already fairly old by Luciano Gattinoni and his group, he has actually described the different conditions that we could be confronted with at the bedside. So we have two different lungs, both with the same total elastance. However, in the case of the stiff lung, about 50% of the power which is imposed by the pressures is taken by the surrounding chest wall, and only the other 50% are taken by the lung itself. But if you have, in contrast, a very soft chest wall, then you see that the majority of the pressures will be used for expanding the lung and not the chest wall. So that means depending on the elastance of the chest wall, the exposure and the stress on the lung tissue is very, very different. There were some investigations to determine the ratio between lung elastance and the total elastance of the respiratory system. And then the normal ratio was determined to be 0.7. So that would be the kind of normal ratio. But in patients, depending on the lung and chest wall conditions, and chest wall elastance, as I will explain later, is of course also mainly determined by the intra-abdominal pressure, which can be high or not so high. The ratio can be very different. So the ratio can, like in this example, be 25 divided by 30, leading in a ratio of 0.83. In contrast, when the chest wall is very stiff, the ratio would only be 0.5. Okay, so when the target is to apply lung protective ventilation, we need to know how much the lung is actually stretched and not, and that, as I pointed out, is not determined by the airway pressure. It's determined by the transpulmonary pressure. And then we are talking about the maximal stretch, and we are also talking about the so-called tidal stretch, the stretch and the mechanical power that is delivered to the lungs with every single breath. And in order to answer these questions, we need to know, how stiff is the chest wall, and then how stiff is the lung. And both types of elastance can, of course, change depending on the physiological and pathophysiological conditions of the patients. So to determine the chest wall elastance and the lung elastance, we need to know the pleural pressure. And because that is a pressure located in a closed system, the pleural is not directly accessible, of course, without invasive measurements. Minimal invasive measurement is taken, which is the esophageal pressure, and that substitutes the pleural pressure. So in order to measure the esophageal pressure, a catheter needs to be inserted into the esophagus, and then it is forwarded towards the heart region of the patient. And then at that position, the pleura is very close to the esophagus, and then the esophageal pressure can reliably be measured. I should also say, and I'm not going into all the details, of course, there are plenty of limitations and things that have to be guaranteed. For example, the filling of the balloon has to be correctly made and also verified and controlled. And also, of course, the position of the balloon has to be located close to the heart. And that is also something that needs to be determined. that is something that I will display later on with some sample data of the PromaVista. Okay, so, and if you have then measured with this balloon catheter the esophageal pressure, then the delta pressure divided by the tidal volume gives you the chest wall elastance. The chest wall elastance is determined by the properties not only by the rib cage, but also by the diaphragm and especially by the abdominal pressure and abdominal muscles. And that is actually the structure where we probably have to expect the largest variation. I would say the elastance of the rib cage itself will not change significantly during the treatment of the patient. But abdominal, as you know, as intra-abdominal pressures can vary and change a lot during the treatment. So if the chest wall is stiff, the chest wall elastance is high, and then the esophageal pressure is also high. So once the chest wall elastance is known, it can easily be, the lung elastance can also easily be calculated, because the lung elastance is basically the elastance of the respiratory system, which you already know by knowing the delta airway pressure and the tidal volume. And then you simply have to subtract the elastance of the chest wall. And then the lung and chest wall mechanics can be discriminated. And another relation and something you also have available with the monitoring of esophageal pressure is, of course, the transpulmonary pressure, and the ratio between the transpulmonary driving pressure and the tidal volume gives you also the lung elastance. And that is also a way to calculate and determine that. And so we could say the driving pressure, the driving transpulmonary pressure is actually the pressure that determines the lung distension, and that needs to be monitored or should be monitored and limited to avoid lung damage during mechanical ventilation. So the transpulmonary pressure is something you can't measure, but you can also calculate it by simply subtracting the esophageal pressure from the airway pressure. And that is this formula, and that is exactly how we also calculate the transpulmonary pressure with PromaVista 500. And the pressure pod. So basically, we used to have a ERT device, which is basically measuring bioimpedance and the changes due to ventilation. And with the new software of our device, in combination with a little box, which is displayed here, it's just a small box that can be attached and connected to the PulmoVista, then we get the means to measure the airway pressure that is needed for this formula, the esophageal pressure, and on the top, we can additionally also measure the gastric pressure. For example, if we use a probe with two balloons, where the one balloon is located in the esophagus and the second one is basically forwarded into the stomach. Okay, and then I would say there are two different conditions that we have to consider here. The one is the monitoring of transpulmonary pressures during mechanical ventilation. As I said, the transpulmonary pressure is responsible for the lung distension, and that's why it should be carefully be monitored. It's calculated by subtracting the blue curve, the airway pressure, and the green curve, which is the esophageal pressure, and then the differential value here is represented in this yellow curve, and that is the transpulmonary pressure. On the top and to the left, we also still have in the same view the monitoring, the regional monitoring provided by PromaVista and provided by EIT. And then we also have here the global impedance waveform. And what you also can see is that in this view, for each of the curves, we are displaying here the end inspiratory value, the end expiratory value, and the driving pressure, the resulting driving pressure. And that is displayed here as parameters for the airway pressure, the esophageal pressure, and the transpulmonary pressure. So for patients with passive mechanical ventilation, the main parameters that you will probably be interested in is displayed in this parameter field, which is the end inspiratory transpulmonary pressure that needs to be limited, and the driving pressure of the transpulmonary pressure that also needs to be limited. So according to publications and consensus papers, here's a presentation of the limits that should be kept and maintained. So the transpulmonary driving pressure should be kept below 10 to 12 centimeters of water, at least in ARDS patients. And it is all during mechanical ventilation. And because you can't set this driving pressure directly, you have to set it by adjusting the airway pressure accordingly, the delta airway pressure accordingly. The second one is the end inspiratory transpulmonary pressure determines the total mechanical stress. The first one was a tidal stress. But the total stress is determined by the end inspiratory transpulmonary pressure. And that should be kept, according to the consensus papers, below 22, at the maximum 25 centimeters of water in ARDS patients. And again, you can't set this value, so you have to set the plateau pressure or the end inspiratory airway pressure accordingly. The last one to be monitored is, of course, the end expiratory transpulmonary pressure. And there, negative values need to be avoided because they may indicate the tendency of the alveoli and to collapse, airway or alveolar collapse. So they should be kept in the positive range. And that, of course, can be adjusted by setting the PEEP accordingly. And here is just the display of the consensus paper that was published in 2016 by an international group of experts in this kind of monitoring. Okay, so just to give you an example, and again, that was also described very early by Luciano Gattinoni and this group, implications for guiding therapy. So what does it mean when you determine on your monitor an increase of pleural pressure? That means that with a constant airway pressure, an increase of a pleural pressure leads to a decrease in the transpulmonary pressure because the structure that surrounds the lung is getting stiffer. And that means that the distension in the lung is somehow limited. So it's basically leading to a decrease of strain and the risk of ventilator-induced lung injury. And then, of course, we could think, oh, then it's a good thing to have a high pleural pressure. But of course, it also means that there's a need for higher airway pressures during a recruitment maneuver to reach a sufficient transpulmonary opening pressure. So that is something that certainly needs to be considered. And then, of course, in contrast to the analogy that I introduced on the first slide, of course, we have to consider very much that in contrast to a tube of a bicycle, of course, in the patient, there is the heart that sits between the lungs, and that, of course, is also affected by high transpulmonary pressures and also high airway pressures. And then, of course, the application of a high pressure carries lots of hemodynamic risks due to the reduction of venous return, but also directly of the heart size. So, and that again implies a possible increase of lung edema, partially due to the reduced edema clearance. And well, the group of Luciano Gattinoni already in 2004 pointed out that for critical ill intensive care patients, it's very important and relevant to assess the intra-abdominal pressure and also the chest wall elastance. So basically, he recommended already at that time that those pressures, this kind of additional information, which is not available on a standard intensive care ventilator today, should be considered. And that is what we now also can do with the PromaVista 500 in combination with a pressure pod. So, taking home message for monitoring the transpulmonary pressure during passive mechanical ventilation is quite easy. The measurement of this esophageal pressure allows to determine the chest wall elastance and to calculate the transpulmonary pressure and lung elastance. The delta transpulmonary pressure should be limited to 10 to 12, according to the consensus papers. The inspiratory pressure should be limited to 20 to 25 in ARDS patients. And the negative, the end expiratory transpulmonary pressure should be kept in a positive range by adjusting the PEEP accordingly. So it should be certainly well above 0 centimeters of water in ARDS patients. Okay, so when you take a look on the waveforms of the esophageal pressure, so the green one, you can basically see that during the inspiration, the esophageal pressure also turns positive. So you could say these two waveforms here, the blue one, airway pressure, and the green one, they're kind of in phase, right? You can see that they're basically reflecting the same pattern. And during spontaneous breathing, due to the activity of the respiratory muscles that tend to create a negative pressure, the physiological breathing, there you will see that these waveforms, the patterns are rather the opposite when the ventilator and the patient are in good synchrony with each other. So that means the delta pressure that is created turns negative, and just a very simple way to detect the pattern, whether or not it was from spontaneous breathing, that the airway pressure and the esophageal pressure show an opposite pattern, basically a phase-opposed pattern. Okay, and the information that needs to be or should be monitored is a little bit more than just to look on the parameter field of for the transpulmonary pressure. Here it's a little bit more complex because now we have a new source of energy, which is a respiratory efforts of the patient. So what is a clinical significance of monitoring the esophageal pressure during spontaneous breathing? It's you can use this information to estimate the patient respiratory muscles effort for the breathing, and also to detect excessive spontaneous breathing. You can also use this information to monitor the efforts during, for example, a weaning trial or spontaneous breathing trial and its variation over time. And you can control the maximum transpulmonary driving pressure because that can be much higher than it would be suggested just by the ventilator when you take a look on the transpulmonary driving pressure during high inspiratory efforts of the patient. So that can, as we know, and there are lots of publications about that, trigger patient self-inflicted lung injury, PCID. But by controlling it, these kind of effects, of course, can be avoided. It has also been described in very many review papers that this information is also suitable for detecting and classifying patient ventilator asynchronies, like reverse, auto, or double triggering. And one thing that I should just mention here at this occasion is the elastance and compliance that cannot be reliably measured during the ongoing spontaneous breathing. That is something that I really should mention here, because it's a large limitation during spontaneous breathing of the patients. Okay, so this is just an example how to monitor spontaneous inspiratory efforts. So if the pressure time product, and that is basically the area under a negative swing in the esophageal pressure waveform. If this area increases over a spontaneous breathing trial, then there is a high likelihood of a weaning failure. With the PromaVista 500, you can monitor both the delta pressure of the esophageal pressure, but also the pressure time product. And this kind of information gives you then, for example, a trend. So we have a dedicated trend page for this delta esophageal pressure. And when you should observe that the delta pressure, which is negative, gets larger and larger, then that means and can be interpreted that the patient is probably decompensating. So he is taking more and more efforts during the weaning trial in order to get the air. And then this is an indicator that this patient, the extubation of this patient would probably fail. Then again, monitoring the transpulmonary driving pressures. So the physiological mechanism of the breathing is that the inspiratory efforts generate negative pressures. We all know that. And in ventilated, but also spontaneously breathing patients, this negative pressure adds actually up to the positive airway pressure, because basically if this esophageal pressure is negative, it has to be basically added, and it's coming on the top of the airway pressure, resulting in the transpulmonary pressure. So that means the combination of mechanical ventilation and the spontaneous breathing that can lead to excessive transpulmonary driving pressures. And that, as I mentioned before, that cannot be detected in the airway pressure waveform. So in this case, for example, we can already tell that at least this value was already exceeding a little bit the recommendations of the consensus papers. In order to look on those this information and the transpulmonary driving pressure more precisely, we have a dedicated page where you can, it's like a trend page, and those of you who are already familiar with the PulmoVista 500, they know that we have some two sliders where we can compare the waveforms at two different time points, and then we are getting the corresponding parameters displayed. So in order, for example, to determine then during spontaneous breathing very reliably the maximum transpulmonary driving pressure, we can basically go to the minimum part and the maximum part. And by doing that, then you're getting the resulting driving pressures very, very precisely. So basically, there are two cursors. You have to put the one at the end of expiration, the second one at the end of inspiration, and then you can read the resulting values in the parameter fields. As I mentioned, the transpulmonary driving pressure should be kept below 10 to 12 centimeters of water. Just a short word about the esophageal pressure time product. It's typically determined either for one single breath, and basically what it describes, as I pointed out, it calculates the area of a negative swing in the esophageal pressure waveform during spontaneous breathing, especially. And then, for example, this value could be compared or monitored during a breathing trial, and then you can easily determine whether or not this value will or will not increase during the breathing trial. If it does, then, as I pointed out before, it's probably a patient. We are monitoring a patient where the weaning is maybe a little bit too early, or the extubation at least. The other way is that you are expanding here the time scale, and that you are basically calculating this value over 1 minute. But I also should say, I don't know how many of you are already familiar with the pressure time product. It has been described in many research papers so far. However, I believe in clinical practice, this parameters rarely used. And then the same view where you can put the cursors and compare, for example, also the flow waveform that might be transferred from the connected ventilator and the airway pressure and the esophageal pressure. This kind of combined information in those parameter fields also will help you a lot to detect patient ventilator asynchronous. And there's also a freeze button available that lets you determine the patterns of the different waveforms in more time. Or you again use this static page. It's like a short trend page, and then you basically can also quantify the differences for the pressures in this view. Okay, so there are two different things to monitor mechanically ventilated patients and spontaneous breathing patients. And again, I'm presenting here a table that has been published in this review paper from 2016 again. The name of the first author is Tommaso Mauri from Italy. Some of you might know the name. And here's exactly a table displayed where we see the different parameters that can all be derived from esophageal pressure monitoring. The clinical significance is described here in this paper very nicely, and also the clinical recommendations. And you can see that some of that I already mentioned here on the slides beforehand. Yeah. And all this information here is basically available in the PromaVista 500 display of the pressures. Okay, so taking home messages for the monitoring of esophageal and transpulmonary pressures during spontaneous breathing. The breathing creates negative pleural pressures or delta pressures. So the negative pressures add up to the transpulmonary pressures, because basically if you subtract a negative value, then it is actually added to the airway pressure. And that is the thing that is not visible in the current monitoring of the typical ventilators without esophageal pressure measurements. Then increasing breathing efforts during the weaning phase. they will increase delta pressures of the esophageal pressure and also the pressure time product. And they are an indicator for a weaning failure. And the combined interpretation of the flow, airway, and esophageal pressure waveforms allows detecting and classifying patient ventilator asynchronies. So this is a little bit more information and more things to consider as compared to passive mechanical ventilation. Excuse me. So just one slide about the clinical significance of monitoring the gastric pressure. The gastric pressure substitutes the abdominal pressure, and I don't know how many of you are monitoring the abdominal pressure, but that is also something that you can do with the PressurePod and the PromaVista. And as I pointed out on the one slide before, of course, the abdominal pressure is one influencing and also variable factor for the determination of the chest wall elastance. It also allows estimating the transdiaphragmatic pressure, something that I believe most of you are not also absolutely familiar with. It's again a parameter that is described in many research papers, but I don't know how many of you have actually had this type of information available. But it can be used for assessing the function of the diaphragm and the respiratory muscles. Okay. Then on the next page, there's an overview of the parameters that can be derived from the esophageal pressure measurement, and that are displayed by PromaVista 500. And as you can see, it's a large list of parameters that can simply be calculated once you know the esophageal pressure waveform. So plenty of new parameters. I have introduced most of them already. And you can see that the only sources of measurements are from the esophageal balloon. And if you have a catheter with 2 balloons, also the gastric balloon. And of course, I should also mention that for measuring the airway pressure with a PressurePod of the PulmoVista, you simply need to connect a IV tube, a line from the PressurePod to the patient system close to the Y-piece, and then you can easily also determine the airway pressure. So it's just connecting 2 locks, and that is it. So something which was described also in the consensus papers and the literature reviews, and there were many, as I will show you, something that has been discussed and also mentioned very often is can esophageal pressure be used for PEEP titration? And there's a very famous study, I believe from 2009, the Talmor study, the EPVEN study, which basically used this approach. And then the question, of course, is PEEP titration with based on esophageal pressure an alternative or even competing method to ERT? Because we also have plenty of publications where ERT has been used to titrate PEEP. And that is something I would like to express here and to discuss. So the study, which is from 2008, is from Daniel Talmor, very frequently cited study. And basically what he did is he compared the esophageal guided group against the ARDS low PEEP table group. And that's also something. So the control group received the low PEEP according to the ARDS net recommendations. And in the study group, the expiratory transpulmonary pressure was adjusted according to the FR2. So basically a very comparable table. However, here the end expiratory transpulmonary pressure was used for the titration. And then what they found is that the mean airway pressure was significantly higher as compared to the low PEEP table. So there was a statistical signal in the results. And then obviously also the total PEEP was much higher in the esophageal pressure guided group. And then, well, they found that the compliance was higher and the oxygenation of those patients were also higher. And they basically concluded that a multi-center trial has to be conducted to determine whether this approach can be widely adopted. And that is exactly what they did in the PEEP-Went2 study, again, done by the Talma group, but now in a multi-center setup. However, in this group, they found that they couldn't demonstrate any significant difference in death or days free of mechanical ventilation. And they had to state that these findings do not support the esophageal guided PEEP titration in ARDS, basically because similar results were possible with in the control group. However, I should state that in the control group, here the high PEEP table of the ARDS recommendations were taken. So of course, the esophageal pressure guided approach can be used for PEEP titration, but it does not, at least not in this patient population, in this setup, did not lead to improved outcome. So, and that is something that I'd like just to present as a thought for you. It's just speculation or maybe discussion, I should say, but the explanation why I believe that for PEEP titration, the region information is very important. And if you take a look on the location of the esophagus in the chest, you will see that it's located exactly in the middle of the patient. So I believe that just by having one single value in the center of the chest cannot be very sensitive for detecting lung collapse or also overdistension, so lung collapse will be located here and overdistension will rather be located in the ventral parts of the lung. And so I believe that is cannot be a very sensitive parameter just because of the location. And as we know, this is really just the pressure at a single spot in the chest and not even an average that is presented by esophageal pressure measurements. That's why at least I find it very understandable that, yeah, regional information provides much better approaches for PEEP titration. So, is ERT superior as compared to esophageal pressure-based PEEP titration? There was a poster from Marcelo Amato's group already in 2017, where he actually compared these two methods in the animal trial. And he used exactly the Talma approach for the control and compared it to the ERT methods where we are balancing the overdistension and the alveolar collapse against each other. And at least on this poster, it was clearly demonstrated that the transpulmonary driving pressure was about 2 centimeters of water lower in the ERT group, and also the non-aerated tissue mass determined by a lung CT was 20% less in the ERT group. So the study results, but we have to be aware that was just a small animal trial, at least pointed out that it could be very beneficial to use ERT for PEEP titration rather than esophageal pressure-guided approaches. But of course, we have to also conclude that as long as we do not have any larger clinical trials on that, it's all still a little bit speculation, and we cannot really clearly, confidently state that ERT is superior so far. Then something on the condition and on the frequency of use of esophageal pressure monitoring that I find is very interesting, and that I just would like to share with you close to the end of this lecture. We already had expert opinions and review papers in 2012, which stated, despite numerous shortcomings, the option to sense the pleural pressure by an esophageal balloon represents the next logical step in a more physiological and individually tailored approach to lung protective ventilation. So I think that was very promising, but in reality, as was described here, and that is from 2014, again, also a large group which published this review paper. They stated that despite plenty of data on the usefulness, the measurements in intensive care have been disappointingly slow. But they again stated that the information that is contained in this measurements, the discrimination between pulmonary and chest wall mechanics, is very, very important. However, in 2014, it was stated that it is rarely used in clinical routine. And the same is true in the same was described in the review paper of 2016. And also in 2018, despite data showing its relevance, assessment of transpulmonary pressure or esophageal pressure is still hardly used in critical care medicine. And in the last review paper that at least I'm familiar with, it was also stated that no trials have definitely demonstrated the positive impact of esophageal manometry in patient outcomes, and that they suggested that this might be one of the explanations why it's not frequently used in clinical practice. So I don't know about you. I would like to ask you, but this is not so easily done with a setup. How many of you are actually frequently using esophageal pressure monitoring? I think the concept and the information that is provided is certainly clinically relevant, as I said, mainly for limiting the transpulmonary distending pressures for the lungs. So my conclusions, the monitoring of transpulmonary pressures allows determining the patient's lung distension, and fortunately, critical values for these parameters that I have discussed in this lecture for passively ventilated patients, I should say, have been well defined in consensus papers. So that is really good. That really helps that users, doctors worldwide will be using those parameters in a comparable way. The esophageal pressure also provides helpful information on the respiratory efforts and the extent of negative swings, especially during weaning trials. But in contrast to ERT, where the first studies at least have already shown benefits in patient outcome, the esophageal pressure guided PEEP titration so far at least could not demonstrate outcome improvements, unfortunately. And I would also suggest that based on those findings and the difference between taking a look on respiratory efforts and the true lung distensions in contrast to regional information as provided by ERT, I believe these two sources of information should be considered for complementary use rather than as alternative approaches. And while experts acknowledge the value of esophageal and transpulmonary pressure monitoring, I believe my impression is, and that is also based on the feedback that we are getting from the market, that it is still hardly used in critical care medicine. Okay, that was the last slide, and I believe thanks very much for your attention and listening. And now I believe it's time for some questions. And maybe
Excellent.
because I can't see the panel properly, maybe somebody can read the questions for me because I can't see properly.
Definitely. Thank you so much, Echo, for this excellent, very detailed presentation. I think you have covered very important topics. So now we would be happy to answer the questions if you have any. Echo, maybe in a few words, you can just summarize once again the clinical relevance of the esophagus pressure measurements. I mean, what kind of patients, what would be the most critical situation in your opinion?
Okay. Yeah, well, I believe that by having the kind of critical limits for transpulmonary pressures, and I'm talking about inspiratory and expiratory and the driving pressure, having these numbers and being able to monitor it for the most critical ill patients, mechanically ventilated patients, that is really, really helpful because it certainly contributes to preventing ventilator-induced lung injury, simply because we can monitor the pressures that are distending the lungs. And the second thing is that, I mean, we see more and more publications on patients with spontaneous breathing. And I mean, there are some good reasons to have this combination, mechanically ventilated patients with spontaneous breathing. We also have plenty of modes in our ventilators that allow this combination, spontaneous breathing under mechanical ventilation. But because the inspiratory efforts of the respiratory muscles of our patients, they cannot be really nicely monitored without knowing the esophageal pressure and the negative driving pressures. That's why I believe that is a second very large benefit that we can basically determine which of our patients is taking so much, so high respiratory efforts that the patients should rather be sedated in order to limit the stretch on the lung that we can also monitor nicely now with the transpulmonary pressures. These are the two things where I believe this is really the important piece of information that is delivered. And I mean, there's plenty more that can be monitored. I should also say, due to the limited use in the clinical routine, and there are some good reasons for that, because we need to insert a probe, a dedicated probe with a balloon. And we also need, every time we do this monitoring, we probably should control the cuff pressure and the balloon pressure, and also the position of the balloon, which might be changed during the critical care of the patients. That is something that, of course, puts some limits in the frequent use of this information. But then, I mean, if the use is limited, it always takes a while until people really get used to it and really consider it to be a standard monitoring tool in their ward. But I know this long-lasting process, of course, also very well, being a product manager for electrical impedance tomography. So the status and the frequency of use and the slow transition phase from research use towards the clinical standard use is a long way, and it will take a time until people are getting more familiar with that. And I mean, both modalities are basically reflecting the complexity of the lung mechanics and of the lung structure. So that is, of course, also something where people that will have plenty of information will partly be overwhelmed with this, lots of information on the complexity on the lungs.
Excellent, Echo. Thank you so much.
Hi again. Well, in the second part of this webinar, I'd like to use our simulation software of PulmoVista 500 to take some real patient data in order to demonstrate our new view transpulmonary pressure analysis. So I first start with a recording of a patient that has been ventilated mechanically without spontaneous breathing. And so that is just the part of the simulation, but apart from that, being pre-recorded data, I can show you all functions and displays that are available when you do these kind of measurements directly at the bedside. So first of all, in contrast to the ERT measurements that are automatically available when you have connected the electrode belt, for the measurements of the pressure pods, you have to turn the measurement on, and depending on what kind of probes or catheters you have connected, you can select whether or not you would like to have airway pressure, esophageal pressure, and if you have a catheter with 2 balloons, you can also select gastric pressures. And in our case, we have all the measure lines in place. So then I just start the recording. And so first of all, you need to go to the view PTP analysis. And as you know, PTP stands for transpulmonary pressure. Right now you see the main view of PulmoVista 500, and that is something I already have introduced. That is basically a dynamic image and a tidal image representing the distribution of tidal volumes for each detected breath. And then we are getting the global impedance waveform that corresponds very well to the volume waveform of a ventilator and the local curves. So the new view for the display of the pressures has a similar structure. Also here we display the ERT information on the same view. So while you are assessing the pressures, you can also take a look on the regional distribution of ventilation. You also get displayed the impedance waveform, but only the global one, not the regional waveforms. On the top, you can configure now whether or not you would like to display the volume information, which is kind of very similar to the impedance information, or whether you would like to display the flow waveform or also the airway pressure waveform from the Medibus, from a connected Medibus device. Then the new part of this view is that we have a waveform field for the display of the airway pressure. And then next to this waveform, we have a parameter field, which displays the inspiratory pressure and expiratory pressure and the delta pressure. Below, there is a green waveform that represents the esophageal pressure waveform. And we have an automatic detection of the expiratory and inspiratory time points, which are used to calculate the parameters. So also for the esophageal pressure, we're getting the inspiratory and expiratory and delta pressures. On these two waveforms, we now can calculate, as I explained in the first part, we can calculate the transpulmonary pressure, which is displayed here in the yellow waveform. And also for the transpulmonary pressure, we are calculating then the inspiratory and expiratory and the delta pressure. And remember, there are kind of limits that have been described in consensus papers which should not be exceeded. Last but not least, if we have the second balloon in place, we can also monitor the gastric pressure that is a substitute for the intra-abdominal pressure. Okay, so when you, for example, so that is basically the structure and the display, and as I explained, for mandatory ventilation, the main thing you're interested is the parameter field for the transpulmonary pressures. Okay. So when you do a more detailed analysis, you can also do this by pressing the button static analysis. And then you can use the sliders that those of you who already are familiar with the trend use of the PromaVista for the ERT related information, you can basically select those sliders and determine an expiratory time point, then an inspiratory time point of the same breath, maybe at the next and inspiratory plateau phase, and then you get also the corresponding parameters, just as explained before, for the selected breath. So with this kind of selection and manual assessment, then you can also determine on this page respiratory system elastance, chest wall elastance, and the lung elastance. And that is all displayed here in this table. So the typical pattern of a patient without spontaneous breathing is that when the airway pressure increases during the inspiratory phase, the esophageal pressure increases as well. So basically, the blue and the green waveforms are in line. They're showing the same pattern more or less, even though, of course, the amplitude might be very different depending on the chest wall and the lung compliance. But that is basically it, what I wanted to explain to you by this simulation file. And now I would like to go to the next simulation file. In order to change the simulation file, I first need to go to standby. Then go back to the configuration, the system setup. Now I'm selecting a patient which was spontaneously breathing. It was an obese patient with a pneumonia, while the patient I just showed just had a trauma and was more or less lung healthy. Now I'm loading the second file. Again, I go to the start standby page, like in the real life condition. I already had activated the PressurePod measurements for the previous file, so now I only have to say start measurements. Then we are again going through a 30-second calibration phase initially, but even in this phase, we can already now turn back to the PTP analysis. And now you see the pressure waveforms again. The big principal change in the pattern that we observe in spontaneously breathing patients is that while you see, and I do this using the freeze display button, while you see the increase in the blue waveform, the airway pressure waveform, then at the same time presumed as the patient spontaneous breathing and the ventilator is in phase, so you do not have asynchronies displayed. But if the ventilation and the spontaneous breathing is occurring synchronously, then you should always observe an increase, a positive slope in the airway pressure waveform, while at the same time you would see a negative slope in the esophageal pressure waveform, because the patient is basically creating negative delta pressures in the esophagus.
due to his own respiratory efforts. So that is a characteristic pattern in a spontaneously breathing patient. And you can also see in the parameter field for the esophageal pressure that the driving pressure is negative. So that is something you only observe while you're monitoring spontaneously breathing patients. And then again, when you, for example, want to detect whether or not the patient is breathing and spontaneously with a very high respiratory efforts, you could again go back to the static analysis and then, for example, determine the maximum amplitude here in the waveform, like for example in this case, and then you can basically see that yeah, the inspiratory pressure is 15, the esophageal pressure 13, and so that helps you to determine the transpulmonary pressure. And also the transpulmonary driving pressures. They might be displayed just being like 4 centimeters of water for the airway pressure, and that is information that is typically displayed on your ventilator. However, in reality, due to the respiratory efforts, you see that the transpulmonary driving pressure is twice that high. Okay. Then when talking about the limitations or the technical issues that could occur while you're measuring esophageal pressure, the one thing is, of course, the balloon filling, but there the recommendation is just to observe the user manuals of the manufacturers of the probes, and then whenever you are not sure about the proper volume, just evacuate the volume out of the balloon and do a refilling with the volume as specified in the user manual of the probes. The second issue is the position of the balloon. We know that the balloon should be located close to the heart, because that is a location where the esophagus is very close to the pleura. And so that is something that can be checked, and this also has been described in consensus papers. And that is something that I also would like to demonstrate you with a different file. That is, and I should also say, all these educational files that I'm presenting right now, they are also contained in any PromaVista device as a kind of training and simulation directory, where all the files that can be used for training and educational purposes are located. So right now, I'd like to show you an occlusion test, because that is exactly what you need to do when validating the correct position of the balloon. So now I'm starting this simulation file, which contains the occlusion phase. And the occlusion has to be done at the end of expiration. And in the spontaneous breathing patients, they will sooner or later do their own spontaneous efforts, and they are displayed then in the waveforms as negative swings. And then during the occlusion phase, the pattern of the airway pressure waveform and the esophageal pressure waveform, they should be more or less identical. And that, if that is the case, then this is indicating that the balloon is located in the right place. So let's take a look here. And so we have a dedicated view or page for that. That is part of this esophageal or transpulmonary analysis view. So here is a button that you can press for the occlusion test. Then we have the refresh button here, that we can then basically use after we have conducted this end expiratory occlusion phase. This page also contains a little instruction or a help text which distinguishes between patients with spontaneous inspiratory efforts and sedated patients. And the text that is displayed here is more or less the same what is recommended in the consensus papers. Now we can clearly see here the occlusion phase, which are these three negative swings. And what we have now to do is we have to use the sliders of those waveforms that you might already know from the diagnostic view or from the zoom function that we have in our trend views. And we can now focus, by using those sliders, we can focus on the occlusion phase. And in this example, there were three negative swings, and we should now be sure and validate that the ratio between the delta pressures of the esophageal and airway pressure show a ratio of 1. The ratio should be, the target is that this ratio is in the range between 0.8 and 1.2. And in this case, that is kind of the perfect match. And that is displayed here in this dedicated diagram. The second parameter that is also relevant is that you can use this section of the airway pressure and esophageal pressure waveforms to determine the correlation, the R square. And if the R square is very close to 1, then this also supports the message that in this case, the balloon was located in the perfectly right position. Okay, so as a last example, I would just like to show you the same when the patient is ventilated mechanically without any respiratory efforts. And that is the last file that I also would like to share with you. So I'm going back to the directory files PressurePod, where the relevant files are located. And now I'm selecting the occlusion test during mandatory ventilation. These are all relatively small files, so it doesn't take lots of time to load them. You again start the measurement. You again have to wait a little bit until the occlusion phase for this patient is also displayed. And immediately go to the PTP analysis view again. And after the calibration phase has been terminated, and we can already open the occlusion test. Okay, so basically this dedicated page for the occlusion test is a very short trend. And as I said, as we can do it for every trend page that we have in the PromaVista, we do not have a moving window here, which is automatically updated, because for the assessment of different maneuvers, and that is a general approach in the PromaVista, we manually can refresh the data, but it's not done automatically, so that you do not lose the section where you might be mostly interested in right now. And so this is exactly the critical thing that you need to do for mandatory ventilation. There, the patients obviously do not take any respiratory efforts and do not create those negative swings that I just presented. But you have to rather do manual chest compressions during the occlusion phase. And in this case, 3 manual chest compressions have been done. And you can just take a look on the patterns of the waveforms and determine where these chest compressions have been performed. That is exactly this phase. So in this case, again, like in the previous example, you can focus here on the and expiratory occlusion phase. Now you do not see negative swings due to the absence of spontaneous breathing, but you create positive swings by those chest compressions, and that is exactly what you can then use. This episode can be used for determining the ratio between the esophageal and airway delta pressures. And in this example, we at least achieved a ratio of 0.9, and that can also be considered to be a reliable measurement because the balloon is also at the right place. Also, the R square is a little bit less than in the previous example, but still it's very close to 0.1 or 1.0, I should say. Sorry, and that is it. So this is a tool for determining the right balloon position, and that is all that needs to be done or at the beginning before you start interpreting those waveforms. What we also have integrated here is a filter function. So we can activate a low-pass filter. Usually for finding the more or less right position, it's actually quite good to have no filter activated, because then you can already take the cardiac oscillations to determine more or less the right position close to the heart, where the oscillations should be the largest. But then after you have found and identified and verified the right position, then in some cases it actually makes sense to use a low-pass filter to minimize the cardiac oscillations that you might see in the waveforms. The last page that we also have, and that can be, for example, used for observing the respiratory drive during a weaning or spontaneous breathing trial during the weaning phase. There you actually can use this esophageal pressure delta trend, and that is the only trend on this page where you can display time periods up to 2 hours. So that is sufficiently long enough in order to follow for example, the negative swings of a patient. Basically, that represents a respiratory drive on those patients, in order to monitor if those negative swings would increase during the weaning phase or during the spontaneous breathing trial, which would be an indicator for weaning failure. So that is basically all the functionality I would like to show you in this second part of this webinar. So the webinar, the contents are over right now, and now at this point I'd also like to thank you very much for taking your time to join, to listening. I hope that this information was helpful for you, and in case that there are some questions they can be asked afterwards, you can also address them to Dräger via email. Thank you very much again. Bye-bye.